Okay, so last time you guys had section 4.1, which is all about ionic bonding. And last time on the call, Emmanuel kind of pointed out, hey, a lot of this is review, which was correct. A lot of the stuff that we're going to start off with is going to be review because we cover a little bit about the basic ionic bonding and covalent bonding and how to do their names and formulas in 10th grade chemistry. So as we go, you're going to see some things are going to be a little bit review, some are going to be a little bit new information. There's kind of a combination as we go through all the different parts of this topic. So today's focus is on covalent bonding. And so the beginning of this is going to be mostly review because, as I said, we talk about the basics of bonding in 10th grade chemistry and kind of what a covalent bond is. What's going to be possibly a review just depends on sort of how far your teacher, whoever you had last year, went into it. We're going to talk about the difference between polar covalent bonds and non-polar covalent bonds. And then we're also going to talk about polar and non-polar molecules and how we sort of determine if a bond and if an entire molecule is polar or non-polar. And so we kind of touch on that in the advanced chemistry classes. But we don't go into a lot of detail on it. We don't spend a huge amount of time on it because usually it's kind of right towards the end of the first semester when we're getting to that. And so depending on sort of how much you remember and how far your teacher kind of went into it, you may or may not have kind of seen this stuff. And then the very end, when we talk about coordinate covalent bonding, that is totally brand new. So we'll spend a lot of time on that end part. So basically here at the beginning, we have our kind of summary of all of our statements for what we need to be able to kind of know and do at the end of this section. And so for this one, we need to know what is a covalent bond and how is it formed? Okay, because when we talked about ionic bonds, they were an electrostatic attraction, but it was between the positive and negative ions. Do you guys remember what those are called? What's the name for the positive ion? Yeah, cation. And then what's the negative anion? Shoot, I just said it. Wow. Y'all can tell it's Friday and I'm tired because I just said negative anion. Wow. Okay, so cations and anions, because there's a full positive charge and a full negative charge because there is an electron lost and an electron gained. In covalent bonds, they're not transferring, they're sharing the electrons, but there is still an electrostatic attraction. It's just not between two different ions, it's between the pair of electrons that's being shared and the positively charged nuclei. And so we're going to look at a little diagram further down and kind of talk about what that looks like and how that works. We're going to just briefly review that we can have multiple bonds with covalent bonds. And we're going to talk a little bit about how having a double or a triple bond affects the bond length and the bond strength of substances, or of molecules, I should say. And then the last little few parts on here are all about the bond polarity. So we're going to talk about how do we figure out bond polarity, and we figure it out by referring to electronegativities. And so we'll be looking at the data booklet on section 8, because right here it says that we can find electronegativity values on section 8 of the data booklet. So if you need to refer to them for answering questions, you can use that. And then we also need to be able to figure out on our applications and skills here to deduce or to figure out the polar nature. So is a bond polar or is it non-polar? Okay. And then when we're talking about bond polarity, we're going to talk about how do we represent that, because if we know that a bond is polar, we need to be able to indicate some way that which side is the side that has the partial negative charge and which side has the partial positive charge. Because that's what polarity means, is it means that your electrons are not being shared equally. So one side of the bond is going to have partially negative charge because the electrons are going to be closer to it. Okay, so here's the little diagram I was talking about. And this just shows kind of just the basics of a covalent bond. Okay, what kinds of elements make covalent bonds? You guys remember? Covalent. You're thinking ionic. Oh, okay. So last time we talked about ionic was one metal and one nonmetal. And covalent is nonmetals only. So typically you're going to have two nonmetals. Okay. When we get into like organic chemistry and things like that, we're going to have lots of molecules with lots of different covalent bonds. So there's going to be more than two. But most of the time it's 2 for what we're talking about when it's just one bond forming. So when we're trying to figure out if something is ionic or covalent, look at the elements. If it's a metal, non-metal, that's ionic. If it's two non-metals, it's covalent. Where you want to look at the electronegativities to figure out the type of bond, you want to look at that to help you figure out if it is polar covalent or non-polar covalent. Because we talked last time about how you look at the electronegativity values to figure out if something is ionic covalent or if it's polar covalent, non-polar covalent. Really, you should look at the types of elements to figure out if it's non-metal or if it's covalent or ionic, okay? But if you've identified it as covalent because it has 2 nonmetals, and you're now trying to identify is it polar covalent or non-polar covalent, that's where you need to look at the electronegativities, because if it's 0 to 0.4, so if it's less than 0.4, or 0.4 or less, that's going to be nonpolar, because if it's close to 0, that means the electrons are being shared equally and there is no partial negative or positive side because they're right in the middle, they're being shared equally. If it falls in that range where it was 0.5 to 1.7, that's going to be your polar covalent. And that means that even though they're both nonmetals and they're both sharing, because one of them has a higher electronegativity value, the difference between them is enough that that one with the higher electronegativity is attracting that bonding pair of electrons more. And so that means that the bond is going to have one side that's going to be a partial negative charge and the other side is going to be partial positive because they're not sharing equally. So this diagram is showing the electrostatic attraction. And so you can see that the electrostatic attraction in covalent bond comes from, here's where my positive's coming from. It's coming from the nuclei in the 2 atoms. And then here where this bonding pair of electrons is, there's an attraction between the nuclei and those electrons, and that's what holds it together. So it is weaker than an ionic bond. Ionic bonds are the strongest type of bond. Covalent bonds are not as strong because they don't have a full positive and full negative charge attracting. It's just the partial charges of the nuclei and the bonding electrons that are being shared. So the next section is just a quick recap on the single, double, triple bonds. Here it's showing you 3 different molecules. They look pretty similar. They all have 2 carbons that are bonded in the middle, and then they have some hydrogens bonded to the carbon. So if you notice, the first one's got carbons that are single bonded, the middle one's got a double bond, and then the one on the right has a triple bond. So as you go from that single to the double to the triple bond, what do you guys notice is happening to the number of hydrogens on the molecule?
There's less hydrogen.
There's less hydrogen. Thank you, Simon. And so what happens is, because we have to follow that octet rule, right? And so everybody wants 8 electrons in their outer shell. So for an element like carbon, carbon can make up to, it's always going to make 4 bonds. Okay, it can make 4 bonds. So they could be 4 single bonds. It could be a double and 2 single bonds, or it could be a triple and 1 single bond. But it's going to be some combination of 4 bonds. Okay. So what happens is when we have molecules like this, these are organic molecules, and we're going to get a lot more into this next year when we get to our whole section on organic. But basically, when you have molecules like this where you have carbons attached to each other, if a carbon single bonded to another carbon, like by default, it has to have 3 carbons attached to it to fulfill that octet rule. Okay. So when we get into organic chemistry, we're going to be drawing stuff like this. Like we're just going to see like lines like this. And like I can tell you that that's propane just looking at it. Okay. Because propane is a chain of 3 carbons that is single bonded. And so this is called a skeletal structure. And so really every time that there's a corner or a point, there's a carbon there. And so they're single bonded. Now, if I drew it like this, that's propene, because now I've put a double bond in there. So when we get into organic, we learn a whole nother system of like naming and drawing structures. And these are the structures that like you always see them like drawn on like the boards in like movies and like TV shows. Like they draw all these weird looking molecules and nobody really knows what they are. But if you know enough about chemistry, you know that sometimes they've drawn them incorrectly because they have like too many double bonds where they can't have them and things like that. But for today, what we're going to focus on is the fact that The double bond and the triple bond, you're adding more electrons that they're sharing, okay? So here, the number of shared electrons increases as the number of bonds increases. And so if you look, what happens to the strength of the bond as we increase the number of bonds? It increases, right? It went from 347 all the way up to 839. What happens to the bond length as you add more bonds? It decreases, yes. So that's kind of what we need to know, that relationship there, that more bonds means more shared electrons, which means that electrostatic attraction is going to get stronger. So the bond strength increases. And as that attraction increases, they're going to get closer together. So the bond length decreases. Okay. All right. Okay. So now polar covalent bonds. Okay. We already talked about it has to fall between 0.5 and 1.7. Okay, to form a polar covalent. Anything less than 0.5 is going to be nonpolar. Anything greater than 1.7 is typically ionic, but I will tell you, be careful, because as I said, if it's a metal and a non-metal, you don't even need to check the electronegativities, okay? Because some people, they rely on the electronegativities and they'll subtract and they'll say, oh, it's 1.6, so it's polar covalent. But if it's a metal and a non-metal, that has to be ionic. So there are some where if the metals and non-metals are close to the center of the periodic table and their electronegativities are a little closer, where you don't get more than 1.7. And so that's why a general rule, look at the types of elements first. And then once you know it's two non-metals, then look at your electronegativities to figure out if it's polar or non-polar, okay? All right, so we need to look up electronegativity. So we're gonna look up hydrogen and chlorine for this example. So I'm gonna switch over to our data booklet so y'all can see that. I don't think I cleaned it off from last period. Nope, I didn't. Let me erase all this from last period. Okay. So we need chlorine and we need hydrogen. So here's, I'm gonna zoom in so y'all can see it. Here's hydrogen. So what is hydrogen's electronegativity on here? Let me scoot it over. Y'all can see the key. There we go. So electronegativity is down here in the center at the bottom. So we find hydrogen's box and we look at it. Can y'all see it? Is it big enough? Okay. So what's hydrogen's electronegativity? 2.2. There it is right there. Okay, now I'm going to scoot over and we're going to look for chlorine. Chlorine's over here on this side. So what's chlorine's? 3.2. Thank you, Renee. So Renee said it's 3.2 for those of you at home joining us. I feel like we're on a game show. Those of you at home, watching at home. All right. So 3.2 and 2.2. So let's go back and fill that in. Okay, so hydrogen is 2.2, chlorine is 3.2. So I'm just labeling these. You don't need to write these numbers on a bond. I'm just labeling it so y'all can see the work being done. But what you do, you're going to subtract. Now you always subtract. You'd always do bigger number minus smaller number because you want your answer to always be positive. Okay. So I'm going to come over here. So 3.2 minus 2.2, that's pretty easy. What's that going to be? 1, right? So we'll write 1.0 just to keep the decimals even. So the difference is 1.0. And if we look, that's between 0.5 and 1.7. So that tells me that this is going to be a polar bond. So then once I determine that a bond is polar, now I need to be able to indicate on the bond, like which direction is the polarity going. So there's two ways you can represent it, and y'all can see them right on here. One of them, you use what's called a vector arrow. And so you always draw the arrow pointing to the element that has the higher electronegativity, because that's indicating that the electrons are going more towards that element in the bond. And so this way you can see that they've kind of drawn it, and it has kind of a plus sign on the other end of the arrow. And that's our way of indicating that that side of the bond is the side that is partially positive, because the electrons are not close to that side. They're closer to the chlorine in this example. The other way you can write it is you can actually use the little symbols for partial negative and partial positive charge to indicate that there are dipoles. And so we use this kind of it's a Greek symbol. It kind of looks like a weird music note, or like a lowercase d that they like squished the line for the top of it. And then you put a plus sign for the side that has the positive, a negative sign for the side that has the partial negative. And so whichever one has the higher electronegativity would get the one with the minus sign, and whichever one has the lower electronegativity would get the one with the positive sign. I like the arrow because I think it's easier to draw. It's quicker, and you know, if you're not used to drawing that little symbol, okay. So for me, the arrow is quicker, so that's the one I prefer to do. But either one is correct as long as you have the arrow pointing the right way or the plus and minus correctly on the other one. All right, so let's skip your problems. Okay, so now that we know how to find bond polarity, now we're going to talk about how do we know if an entire molecule is polar or nonpolar? Because sometimes molecules are just made up of one bond, like all of our diatomic elements. So here's oxygen, here's O2, here's nitrogen, N2. Oxygen is just 2 oxygen atoms double bonded. Nitrogen is just 2 nitrogen atoms triple bonded, and all of the other diatomic elements are the same. So our hydrogen, and then all of our halogens. So we got fluorine, chlorine, bromine, and iodine. So all of our diatomic elements, they're all just that atom bonded to the same element, the same atom. All the other ones are single bonds. The ones I wrote on there, those are single bonds. The only ones that are multiple bonds are the 2 that are already drawn on here for you. But either way, it's still just that element bonded to itself. So by definition, or like kind of by default, any of these diatomic ones, they're always going to be nonpolar, because if we subtract the electronegativities, it's going to be 0, because, you know, we just looked up hydrogen, it was 2.2. So 2.2 minus 2.2 is 0. So kind of by the fact that they're bonded to themselves, they're always going to be a difference of 0, and they're always going to be nonpolar. So all the diatomic molecules are all nonpolar molecules. Now, we have molecules like this one over here on the right, that this is not one bond. This one actually has 4 bonds in it. This is CH4, which is called methane. This is one of our organic molecules that we'll get to later on in our curriculum. But methane is a carbon, and it's single bonded to 4 hydrogen atoms. So what I need to look at is I need to look at the individual bonds within the molecule, because if there are polar bonds in the molecule, then it might be polar. But if all the bonds individually in the molecule are nonpolar, then like by default, that molecule is nonpolar. Because if there's no polar bonds, the whole molecule cannot be polar. So what you want to do is you want to kind of consider each bond separately. So I'm going to kind of put a box around one of the CHs. That's one bond. So I would need to compare the electronegativities of carbon and hydrogen in order to figure out the polarity of that individual bond. Now on this molecule, the other 3 bonds, they just all happen to be CH as well. So really I only need to do it one time, because all the bonds are the same in this molecule. If you had something different, like if one of these H's was replaced with like a fluorine or a chlorine or something like that, you'd have to do the calculation for that bond separately. All right, so we're going to go back and look up carbon and hydrogen on our data booklet. So carbon or hydrogen we already know is 2.2. So here, let's come over here. What's carbon's electronegativity on here? 2.6. Okay. So now let's go back and subtract 2.6 minus 2.2. And so when we subtract, we get 0.4. And that falls into the range of nonpolar. It's right on the edge, but it technically is nonpolar, okay? Because remember, nonpolar is 0.4 or lower, down to 0. And so because each individual bond in here is nonpolar, that means the entire molecule is going to be nonpolar, okay? Now, the next little section is what happened, like, because it is possible to have a molecule that is nonpolar, but inside the molecule, there are some polar bonds. Okay, there are some situations where this happens. The example we're going to look at is carbon tetrachloride. So it's CCl4. So it's a carbon and it's single bonded to 4 chlorine atoms. Okay, so we would do the same procedure. We would kind of look at each bond individually. And so we've already looked up both chlorine and carbon. Chlorine earlier was 3.2. Carbon we just looked at was 2.6. So if I subtract those 2, what do I get? Who can do that math in their head? Yes, 0.6. So that's out of our range of nonpolar. That's now into being polar because polar is 0.5 to 1.7. So that's why on this molecule, they have drawn in all those vector arrows because the CCl bonds, each of those bonds is a polar bond. And notice they all have the arrows pointing towards the chlorine because chlorine has the higher electronegativity. And so that means in this molecule, all the outside areas, those are the areas that are partially negative. The carbon in the center is partially positive. Okay. But even though those individual bonds are polar, because this molecule is symmetrical, and when I say symmetrical, I know that right now you're like, it doesn't look symmetrical. Like I can't draw a line in the middle of it and it looks the same. But if we look at it in 3D, it actually is. Okay. But on paper, it's a little harder to tell. And so if a molecule is symmetrical, that means that it had, number one, it has all of the same element bonded to the center. So this one has all 4 chlorines. And number two, it does not have any lone pairs on that atom in the center. Okay, so sometimes if there's lone pairs in the center, that's going to make it polar just because that's going to affect the shape of it. And that's what we're going to get more into next week is the different shapes. And so it's a little bit more of a review from last year, but we kind of extended a little bit more with the information. So because this is symmetrical, that means that all of these bond polarities are going to cancel out. And so we say that the molecule has no net dipole moment. So if you're asked to describe like, how is this molecule nonpolar when it has polar bonds inside of it, you would say that because all of the bond polarities cancel out, the molecule has no net dipole moment. Because what that means is that, yes, there are some dipoles in each individual bond, but they're evenly canceling out because of the shape of this molecule. So what happens if we have a polar molecule? A polar molecule might look something like this. So this one, we have CH2Cl2. And so this one is similar, the same shape as the last two. It's still got a carbon single bonded to 4 things. But because they're not all the same thing, and this carbon chlorine bond is polar, this makes the whole molecule polar. Okay, because the first example where we had all hydrogens, they were all nonpolar bonds. In the second example where they were all chlorines, they were all polar bonds, but they all canceled out. In this one, 2 of the bonds are polar, 2 of them are nonpolar, and so there is a net dipole moment. And so you might be asked to indicate like which direction is the net dipole moment, and you do it based on those bond polarities. So for this molecule, the net dipole moment is going this direction because that's where the bonds that are polar are kind of pointing kind of up and to the right-ish, or to the left, sorry. And so because of this, it's not symmetrical because I got 2 hydrogens and 2 chlorines. So the bond polarities don't cancel out, and therefore it has a net dipole moment. And that net dipole moment can be represented by kind of drawing an arrow like that over the whole molecule. So that means that over here, this side of the molecule where these 2 chlorines are, that's going to be more negative. The side of the molecule over here where the hydrogens are, that side's going to be more positive. All right, so last section, this is the coordinate covalent bond stuff, okay? So normally covalent bonds, we said they share electrons, but in a regular covalent bond, what happens is each atom donates 1 of those electrons to make that bond, okay? Each of them has a single electron in their valence shell, and they come together, they each share their 1, and that creates that pair that creates the bond. In a coordinate covalent bond, both of the electrons that are being shared, they both come from the same atom. So that means one atom did not have any electrons to share. And so the other atom is going to use both of the ones it has to create the covalent bond. And so that's why it's coordinate covalent, because the prefix co means together. So covalent literally means like valence electrons coming together, and coordinate means that they're coming from the same atom. That's kind of a clue there with the prefixes, with the co stuff. So these are the 3 that you guys need to be familiar with. You need to know how to draw their Lewis structures, okay? And you need to understand where the coordinate covalent bond is coming from, okay? So the first one is CO, which is carbon monoxide, which you might have been hearing about a lot in the news lately because of our recent winter weather. There were people who had lost power and it was so cold that they went out to their cars to like get some heat. And because of that, they let their cars run in like a garage that was enclosed. And combustion engines in cars, they're doing combustion reactions. So they're producing carbon dioxide, but also a lot of times carbon monoxide as well. And so if you do that in an enclosed space for long enough, then it's going to take away all the oxygen and you're going to suffocate because there's no oxygen. You're breathing in the carbon dioxide or the carbon monoxide, which is poisonous. And you don't really know it because it doesn't have an odor and it doesn't have a color or anything. So it's really, really dangerous. There's a lot of houses and apartments now that are like more modern that they not only have smoke detectors, but they have carbon monoxide detectors in the houses as well. So carbon monoxide, we got one carbon, we got one oxygen. Let's see who remembers anything from last year. How many valence electrons does carbon have? Anybody remember off the top of their head?
5.
Yeah, we got it. 4. Good job, guys. All right, so 4, because it's in group 14. So I'm going to draw 4, and they're all single on carbon. Carbon's electrons are single and ready to mingle. That's why it can make so many bonds, you guys. And an oxygen, anybody remember how many oxygen has? Let's see. Anybody on our call?
6.
6. I think that was Simon. Was that Simon or was that Emmanuel?
That was me, miss.
Okay. All right, so 6. So here's what they look like. So normally, carbon, when it bonds with oxygen, normally it makes carbon dioxide. But what happens is sometimes if you're in an oxygen deficient environment, there's not enough oxygen for it to form a bond with 2 oxygen atoms. And so that's what happens in like combustion engines. That's what produces or what causes pollution. Because if there's not enough oxygen around to make carbon dioxide, it'll make carbon monoxide instead. And it's called incomplete combustion. And we learn a lot more about that when we get to our organic chemistry section. But what's going to happen is normally carbon's going to say, okay, well, I'll share, this one will make one covalent bond here. And then here you have another one. So I'm going to make another covalent bond here. So it's going to normally make a double bond. Okay. And then usually if there's enough oxygen, another oxygen atom will come in and it'll make another double bond with that one and it'll make carbon dioxide. But if we don't have enough oxygen, then what happens is it has to bond because we don't like single electrons. Remember, everybody wants to have pairs and be stable and all that good stuff and have their octet filled. So what happens is, I just noticed I left off an electron here on oxygen. There we go. Y'all didn't say anything. Y'all let me draw 5 electrons and didn't say anything. All right, so what happens is there's no more single electrons on oxygen. So carbon says, okay, well, hey, look, I still have 2 electrons left. Let's put them together and then I can bond to you with those 2. So that's that coordinate covalent bond. And so the actual Lewis structure is a triple bond like this. Okay, so that's what the actual structure looks like. It's got a triple bond and then the oxygen still has those 2 lone pairs on it. And so where the coordinate covalent bond comes in, it's that third bond. It's the triple bond. The first 2 bonds are regular covalent bonds. The last one is the coordinate covalent one, because both of the electrons that formed it came from the carbon. Now, for the other 2, these other 2 are polyatomic ions. Okay, the first one's a hydronium ion. The other one is the ammonium ion. We see these a lot when we're dealing with acids and bases. Okay, so when we get to our section on acids and bases, we're going to see these pop up a lot. The hydronium ion forms when water takes on a hydrogen ion from an acid. And the ammonium ion forms when ammonia, NH3, takes on a hydrogen ion from an acid. Okay, so when we get into like solutions with acids and bases, we're going to see these pop up a lot because hydrogen ions are going to be getting donated and things like that. So what happens here is on this middle one is normally, so we have 3 hydrogens. Do you guys remember how many valence electrons hydrogen has? 1, yeah, that's the easy one. So it's got 1. And then oxygen, that's still oxygen, so it's still got 6. So normally hydrogen, oxygen, the most common thing they're going to make usually is water. Okay, so 1 hydrogenal bond here, 1 hydrogenal bond here, and typically you'll get H2O, you'll get water. Okay, but we got an extra hydrogen. However, here's the problem though. Notice that this is an ion. It's got a +1 charge up here. If something has a positive charge, that means that it lost an electron. So in reality, this is not a third hydrogen atom. This is a hydrogen and ion that's going to come in here. So that third hydrogen doesn't have any electrons to give away or to share. And so what happens is oxygen says, well, hey, I can still bond to you because look, I have 2 pairs of electrons. So I will use one of my pairs and I will share that with you and we can bond. And so that is the one I just wrote in purple. That is the coordinate covalent bond. And so when you have water reacting with or taking on a hydrogen ion like this in an acid solution, you end up with this hydronium ion where you have your oxygen in the center, and then that oxygen is single bonded to 3 different hydrogens, and then it still has that one lone pair on it, the one that it did not share. And then because this is a polyatomic ion, we do need to put it in brackets and put its charge up in the corner. Now the last one is going to be similar to this. It's just got nitrogen and hydrogens instead of oxygen and hydrogens. But it's going to be a kind of a similar concept because what's going to happen is we have nitrogen and we have 4 hydrogens. Hydrogen has 1, but just like on the other one of the hydrogens is an ion. It's not a hydrogen atom, so it doesn't have an electron. Now, nitrogen, anybody remember how many valence electrons nitrogen's got?
5.
5. Oh,
5.
it's got 7 total, but it's only got 5 because it's in group 15, 5 valence. The other 2 are on the first energy level, so they're not valence electrons. All right, so 5 for nitrogen. So what happens normally when you have nitrogen and hydrogen, the 3 of these hydrogens are going to bond with the 3 single electrons on the nitrogen. And usually you get NH3, you get ammonia, which is like what's in like Windex and glass cleaners and things like that. It's a base. But sometimes when it reacts with an acid, it's going to take a hydrogen ion from that acid. And so what's going to happen is the nitrogen says, hey, I have this other pair of electrons up here. I'll share that with you and we can bond that way. Okay. And so that last one, that 4th one, is going to be the coordinate covalent bond in this one. All right, so we end up with N and it's single bonded to 4 different hydrogens. And then again, because this one's an ion, we put it in brackets and put its charge up here. So coordinate covalent bonds are important because we saw, like in our last in topic 3, when we got into the HL stuff and we had the ligands. You guys remember the ligands and the complex ions? A lot of those form from coordinate covalent bonds because something is going to share its pair of electrons with something else to form the ligands and the things in those complex ions with the transition metals. All right, anybody have any questions for today, or do you guys want to